The mechanism of halogenation is very similar to hydrogenation. And you can see sort of embedded in the name there that we're going to be dealing with halogens here, typically chlorine or bromine. And when we do a halogenation, in a very similar way to what we saw with hydrogenation, we're adding an X, a halogen, to each carbon of the two-carbon alkene system. However, this one occurs by an anti-addition, where the two halogens come from opposite sides of the molecule. And that has to do with the unique intermediate that's formed. So let's look for a second at a ring-shaped alkene like this, where we could talk about adding a halogen. Now, oftentimes you'll see it written just like this, with no solvent listed at all. If there is a solvent here, it has to be not water. And we'll see why in a minute, but common solvents here are carbon tetrachloride, CCl4, or any number of other things, chloroform, any organic solvent that can dissolve everything but is not water-based. The intermediate that happens here is essentially what we would have expected if we look at our earlier mechanisms and we redraw our bromine like this. We have our nucleophilic double bond that's attacking one side of this molecule, but ultimately what happens is that in contrast to what we saw earlier, the bromine atom is so large that it ends up itself sort of rejoining back to the molecule. And so we end up with the bromine being attached to both in what's called a bromonium ion intermediate. That IUM ending, just like you learned in Gen Chem with the ammonium ion, that just means positively charged. So we end up with this, and our other now bromide ion, having been released from that initial attack, will attack one of the two carbons to form our final product. Now this is where we need to think about stereochemistry. The bromonium ion bromine is somewhere in space. It's either forward of the ring, the way we're looking at it, or it's backward. We don't know which one. In this case, in this molecule, it doesn't matter. So I'll just draw it as having been forward. Well, that means that the most obvious place for this new bromine to attack is from the back, the opposite side. That's a sterics kind of an argument. It's less cluttered back there. There's less bulk. It's more accessible. And so what we'll end up with now is my one bromine being attached to the ring where it was in the first place, and my incoming second bromine being attached on the opposite side. So if I kind of color code those guys, say my red bromine is here, and my initial blue bromine is still here. And so we've accomplished an anti-addition. Well, what happens if we had water in the mix? And I said earlier that for a proper halogenation, we can't have water around. If we do have water around, it's sometimes called a hydrohalogenation. So water and X2. The first step of that mechanism is exactly the same as what we saw before, and that we have our nucleophilic pi bond attacking one half of the X2 molecule to give us the halonium, in this case bromonium ion intermediate. But the difference comes when we get to the second step. If I have water around, water is a reasonable nucleophile too. And so now I would end up with a competition. I would get some of the X2 addition product, just like we saw before, but I would also get some where water serves as my nucleophile in that second step. And so I would get a secondary product here that would show a bromine attached in one place and an OH group attached to the other place. That OH would come from addition of water and then deprotonation by the solvent, like we've seen in earlier mechanisms. So if I want to get the X2 addition product, I can't have water. If I do have water present, I'll get the hydrohalogenation product. Both of them are valuable reactions. We just have to consider that bromonium ion intermediate is susceptible to nucleophilic attack from anything laying around. So the bromide ion or the water can both be reasonable nucleophiles here.